to share some of my thoughts and experiences and hopefully learn from the community today. So I'm Amir. I'm a postdoc research fellow currently at Stanford University at the normal course called biomechanics lab, so it's got Phillips group. And also I'm a postdoc fellow at the Department of Technical Physics at University of Eastern Finland. A Marie Curie fellowship, so we have Haas Institute and then we have Outgoing Phase Institute. That's why I have still both affiliations. So a little bit about my background. So better to introduce myself. What I've been doing during my PhD and now as a postdoc to develop multi-scale modeling pipeline, going from some data like motion data, medical images to musculoskeletal models, estimate joint level biomechanics, go to finite element models, how to link these models, then estimate the tissue level biomechanics that we think they govern the degradation response of the tissue, specifically cartilage or menisci and ligaments. And we have also used this pipeline to first validate those and then to use them in personalized rehabilitation applications to discover their potentials, like data training, ACL reconstruction, and surgery planning. And currently, I'm a little bit also focusing on machine learning applications, first to reduce our need on high fidelity data in many data sets or many cases in clinical applications. We don't have access to MRI, high fidelity MRI or motion data or force plates, and also try to use machine learning to make these pipelines faster and hopefully more robust. And briefly, some of the tools that I've developed, one of them is an automated and robust modeling pipeline that goes from the MRIs to the models in a few minutes, like in 10 to 15 minutes, compared to weeks and months of modeling, including auto segmentation, processing the geometries that we also heard from Scott's work, and meshing, assigning the material, assembling the models with just a couple of clicks. So my aim is to just keep things as simple as possible at a level of just a couple of clicks and not terminal commands. And also trying to develop tools to integrate these different modeling modalities, different musculoskeletal modeling pipelines, content modeling pipelines, and how to link the models. But yeah, we as a modeler, in our research, we are now able to go from body level biomechanics or mechanobiology down to tissue level. We even go to cell level. We add the pain, we add inflammation, and the aim is to predict the tissue degeneration or regeneration response, how to provide like personalized medicine. But as we discussed and talked in the previous session, I think quite lots of topics here I'm repeating from the previous session. So when we go to the clinics, what we see is that they use very simple models back to like 80s or 90s, just multivariate dynamics, and they get simple parameters like kinematics and kinetics. And I think in the IT, when something works, just don't touch it. Also in the modeling, if the model works, don't touch it. So yeah, and one of the concerns that we see why they don't use it in clinic, when you explain this to a clinician or a surgeon, they're very excited to use our models, but they want something simple. They want something robust. So and credibility is one of the issues that we see there. When you talk to them, yeah, they're excited. When they start ask questions, and when you say that, yeah, we don't know how to set the ligaments, and they change the results by 30%, the material parameters 300%, huge amount of uncertainty. This model depends on what gender you're on, what's the age of the subject. But when you look at the simple solutions, doesn't matter how old the subject is, pretty much. Yeah, of course, there are still some assumptions, but overall, what they want is that just plug and play. We heard about the 10 rules in regular practice. I wanted to add a couple of more here based on what I think. So first, the background of the mind. I think one principle is that we go through the needs finding and concept creation even before we try to define the context clearly. This is a separate course in some of the universities. I know many successful companies are formed based on these needs finding. Essentially, students just go on to campus, to hospitals, see what they need, make a list, try to shorten the list and work on the solutions. This is very valuable for us in terms of credibility. It avoids over-engineering or something under constraint models. And it helps us to also know what verification and validation level or uncertainty quantification we need to answer to those questions to meet our needs. And also, it's a bottom-up approach. Sometimes in many research these days, we don't have this bottom-up approach. So we have some PIs, we draft the grants, and then we have a huge gap between our research and the clinical need. And the other thing that I think is very important for us is to be robust. And that's one thing that as we make models more complicated, so we don't have the robustness. The same model sometimes doesn't run in a different computer. We run on models on servers with ECC on, with many other features on. When you go to a workstation at the hospital, the model doesn't work because we haven't thought about it. Or the pipeline is too complicated that we can't run the model. One thing that is also mentioned in ASME that sometimes we don't explore it or try to explain it or include in the research is to map out the model's risk. I think it's also one of the important aspects that we can include in this OpenNE pipeline. So one is that the model influence was a contribution of the model to the decision relative to other available evidence. Of course, we want to increase it when it goes to, for example, clinical use or surgical planning. But the other thing is that the decision consequences. What's the significance of an adverse outcome resulting from an incorrect decision? And we know that we have lots of uncertainties in our models that may lead to decision consequences. And clinicians, essentially, they don't like it and they want to avoid it. The list is pretty long. I just try to pick some of them turning red that I think we challenged most. And sometimes we have yet no tools to go through those and try to validate our model. Of course, one is the data. We talked about it a lot. I don't want to go into details. Sometimes we don't have data for direct validation. One concept also that I liked from the quantum mechanics is that sometimes when we try to measure something in vivo, we're just increasing the errors. So sometimes we need to also consider indirect validation. We have been using like quantitative medical images. It has also its own limitations. For example, you go with the T2 map. We still are not sure the T2 that we get from a Siemens machine is the same as a GE machine, is the same as a Canon machine. There are some research going on in this field as well. One of them also I'm involved in, so we are going all around Finland, not me, but the research group. I'm just helping them with some of the analysis to see if we scan the same knee in different scanners, do we get the same T2 map? Or do we get the same T1 row map? Because that's also one thing that we use a lot in our validations. And the other thing is that sometimes we have a lot of data, but we just don't know they exist. Or we know that from all across the globe, there are fantastic data sets. They're in some publications, but you cannot find any traces. Even some part of the data from OI data set, like imorphics, imorphics, which is a very fantastic manual segmentation of, for example, menisci. It used to be on some NIH data servers, but you cannot find it anymore. All the ways goes back to one person at Stanford. And if you want to use that data set, you should know that you need to achieve that person. So perhaps if this OpenNEs could provide some harmonized metadata, people can use that to share the metadata, but not the data set. And you can store the data set wherever you want, but you have a place that shares the metadata. And it also makes it easier to access the data or reach out the person and make some collaborations and use the data for whatever reason that they cannot share the data. And then the other limitation that we have is the raw data that we have. They are in different sequences. Even the MRI that we have very established, like DICOM file format. Still, when you get the data, you don't have a single library that can deal with these data sets. In some one, the DICOM headers, they use like echo time to report the echo time. Some of them, they use private tag. And still, that's a challenge when you want to use the data to validate your models. For the mocap data, it matters how you filter the data, how you fill the gaps, even how you place the markers. So all of these are concerns when we deal with validating our models. And I think the most frustrating thing is that the data sets are in different formats. And if you want to use different data sets, it's a big challenge and it takes a lot of time to pull out the data, to process the data, and feed it into your model. I think one of the important things that OpenNE can do is to provide some harmonized method. We have, for example, many toolboxes. I just named them here two, MotoNMS, which is a great for motion analysis data. I think the latest update is 2015. So essentially the new data and using that. At biomechanics, developed at Stanford is a great example as well. It's again limited to motion data. it has its limitation, but it's a good example that how they use these tools. So you can put all your motion data and subject data into single file and just move it around and use different classes to use the data also for machine learning approach. But aside from the data, depending on which software you use, you often get different outputs. One example in smooth modeling, OpenSim, for example, versus Anybody. In Anybody, pretty much you have a single model, and all the researchers use the single model. Maybe it's a benefit of not being open source. In OpenSim, you have a bunch of models, so it takes time which model to use. You need to know how they validated each model, what data set used to validate. But here is an example that we use the same model, the model that validated on the same data. But again, you see that the same grand challenge data, but we see that still, if we feed the finite model with these two models, we end up with different results. That's, I think, one of the concerns of the credibility of the model. So, and then we have some other constraints in our computational models, which is the underlying numerical method. Even using single software like Abacus, if you use different contact mechanisms like node to surface or surface to surface, you get different contact pressure. You can't do anything about it. There's like 10 to 30% error in that. And we are interested to use more complicated material model, and essentially the node to contact is the contact that we can use. We have no other option. So hopefully we have some tools like FBio that we can work on that, address some of these limitations with the contact. We are using elements that are designed to analyze stainless steel, but we use that to analyze the cartilage. We are able to modify our elements in, for example, Abacus, but FBio is, I think, a valuable asset and tool that we can tailor those more towards our need. The other thing is about when we create a model, still it's pretty subjective. Depends. You segment the tissue, depends how much you smooth the surface, you get different results. So if you see the same vertebral disc, so if you don't smooth it, probably you're not able to run the model because of those sharp edges. And if you smooth the surface to be able to go towards the robustness, then you will miss the whole point, which is the constant stress concentration at the region of interest. And now OpenNet, I think, can provide some like harmonized pipeline that people can use it to at least run things consistently. Or let's say we create the models in the same way, but also that it's important how we attach them together. Here, try to link the muscular model with the finite model. But if you run the finite model with kinetics, you will end up with this distribution of the stress on the cartilage. And if you use kinematics from the MS model to run the FE model, you end up with a different distribution of the stress. So if you want to make a decision based on these, where the degradation happens, you will end up with different conclusions. And if you want to provide some personalized medicine, essentially you are doing something else, or at least inconsistent. So again, I think we need something to democratize these, or at least provide certain tools that if you use this, essentially you are consistent with the rest of your modeling pipeline. And on top of these, the material parameters is a huge field to cover. I think it's beyond what we have now here in 10 minutes. We have some calibration pipelines, but again, each group are developing different calibration methods with different assumptions. Depending on which one you use, we will end up to different conclusions. And lastly, about these, the robustness, which I personally is very important for me, and most of my efforts have been to go through some robust pipelines. We know that as we increase the higher, as we use higher effective dimensions in our models, we produce more uncertain estimates. Or in other words, lower dimensionality exhibits better robustness. And we see that in machine learning as well. So as an example, if we use a simpler musculoskeletal model, we can run pretty much, the default is that this model runs like several seconds, whatever activity you run. But there are certain limitations. You try to add ligaments, you try to look at the like contact mechanics, add those into your model. But essentially, when you try to run the model, usually the default is that it doesn't run. You need to do a lot of tweaks to be able to run the model. And of course, it takes a little more time. So when you go towards the clinic, there's always a trade-off. Could we keep simple models that runs, or we go to the models that you need a lot of tweaks. And same thing as we have seen also in the finite element models. We know that we need certain complex model, like we need elasticity, we need fiber reinforced material to capture the dynamics of the tissue. But we have also shown that some of simpler material model, but calibrated to those, are able to replicate that behavior for us if you are interested in the bulk response of the tissue, but not at the tissue or cell level response. But in comparison, the model on the left, it runs in 20 minutes. You can run it in several GPUs, CPUs, but it's a bit simpler. But the more complex model, usually it doesn't run. It takes like half a day, 1 day to run the model, and you need to spend like up to 1 year to converge the models. Due to which we see often, like until a couple of years ago, many theses, many works working only with one subject. But now, thanks to automated pipelines, to streamlined processes, we are able to run whatever number of subjects that we have in the data set. One of my suggestions that I've always been thinking about is a kind of modeling package. So what I found that was closest to my idea was the Internet of Fair Data and Services. So essentially, it has 3 parts. One part is the data. So if we try to make our data set harmonize, we develop some tools so we are able to read the data automatically from different data sets. It doesn't need that we copy all the data sets in one place. You need budget for that. We need resources. The data can be federated in different servers, in Europe, in different continents. But we have tools here that you can read those data sets. And then we have also provided some services there. It can be a portal, either local or on the web. So we can connect each of these tools and do our analysis. And researchers can then put their tools on those. It can be like a segmentation tool. It can be a meshing tool. It can be a finite model. It doesn't need to be also open source or a closed source. It's from FBio, it's from Abacus. So we define some sort of API so they can talk to each other. You need to have certain inputs and certain outputs to work on those. One example that I always is on my background is Simulink in MATLAB. Probably many of us have worked with it. So you have certain tools, you just need to put them, connect them together, set some parameters, and then you are pretty much good to go. You hit the button and it does the analysis for you. What I try to do, for example, in the toolset that I develop, I try to keep it modular. So you can replace your MRI processing there, use the rest of the toolbox. You can do your own segmentation, use the rest of the toolbox. If you want to do reprocessing in some other way, you just drag and drop it there. This is a kind of hard-coded GUI, but it's pretty much transferable to that kind of like system like Simulink. And I know that one PhD student in Imperial College, I did last year, he was working on like a Simulink pipeline for every kind of modeling that you want to use. And that could be a nice start here. The same thing we can do with the models. Either it's from FBio, it's from Abacus. We have the possibilities. For example, if you want to use, this is how I now do it. So you can process your mesh, add it, or like attach it to the whole body of the model. Someone wants to work more on the context, so you update that part, attach it to the model. So again, modular design will help a lot. So we can combine all these modalities and different scale. Just to wrap up, I think still uncertainties play a crucial role in the credibility of our models. Simulations needs to be more robust, I think, both in development and more also in the execution. And I still think that it's good that we still consider models as simple as possible, but not simpler. So we need to keep certain accuracy level. And the modular system or ecosystem, that's one of the suggestions. This will help us to facilitate access to the data, to the models, the tools. It can support different pipelines. And eventually, I think it also helps that we start to develop some standards in the models in terms of inputs, outputs, how we link the model. And one of the things that I didn't touch on is very interesting for me too, is how we keep it sustainable. So I think it's a session tomorrow we have. So how we can keep this sustainable also is interesting to me. So we need to keep these repos alive. So sometimes a student graduated, the repo just remains there. And open source, is it the best solution or not? I'm still not sure. Sometimes we should not focus too much on being open source, to be open to other tools we have there. Include also anybody group, include Abacus guys. And of course, sometimes those work better for certain needs. For example, we know that for certain applications, we need to use Abacus. We have no other options. Even ANSYS, others won't provide for us that kind of scale of the model. If you go to, for example, nanoscale, Abacus pretty much is the only option that you have. Then thank you for attention.